Okay, this brief video shows what a total differential is and how we use it in economics for several different purposes. So a total differential is going to be defined as the change in y, or the result of a function, the change in y that occurs when we allow x to change in a bivariate relationship with one x and one y. So if y is some function of x, the definition of the total differential can be thought of as the change in y that results when we allow x to change. And we can express that as a rate of change, that is the change in f from a small change in x times some actual change in x. Okay, so when we multiply the rate of change by some actual change in x, we get the total change in the value of y that results. Intuitively, this I think is actually a useful way to think about what a total differential is. However, if you are uncomfortable with that, you can simply memorize the definition, which is this. Okay? If we apply this to a specific functional form, let's suppose that we have y equals log of x, and we want dy, the change in y that occurs when we allow x to change. This is going to be equal to 1 over x, that's f prime of x, times dx. Okay? This becomes important later on when we're looking at logged models in econometrics, because anytime we see d log x, we could have jumped right to d log x here, we can write it as dx over x. Okay, so we're going to see that a bit later. If we wanted to apply this to a multivariate context, which you see in a number of other applications, okay, typically in our theory classes, if we have y equals f of x1 comma x2, we have a multivariate equation, and the total differential is going to have an extra part to it. It's going to be the change in f when x1 changes a little bit times some actual change in x1 plus the change in f when x2 changes a little bit times some actual change in x2. So when we have multiple variables like this, the total differential is really asking the question, how will y change when we allow a change in x1 and x2 simultaneously? And it can be expressed like this. Most of what we see in this class, however, is going to be that bivariate form of the total differential, and it's going to be in relation to logs. So when we see, for example, y equals log of x, and we look at dy, and we know that that's 1 over x times dx, okay, we can then stop and look at the meaning of this. If we have the change in x and we're dividing by x, this is almost the percent change in x. If we multiply this by 100, that would equal the percent change in y over the percent change in x.